So let A be a square matrix with corresponding cofactor matrix C. That's a D. The adjoint of A is the matrix ADJ of A is defined to be equal to the transpose of the cofactor matrix. So the adjoint matrix is the transpose of the cofactor matrix. So adjoint, I can't write a D for some reason. The adjoint is the transpose, just in words, of the cofactor matrix. And there's a very important result which uses this definition. But before we get to that, let's do an example. So here's the definition. So to calculate the adjoint of a matrix, you have to first calculate the cofactor matrix, and that's the hard part, and then you just take the transpose. That means you just swap the rows and the columns. So let's say A is the matrix 3, 2, minus 1, 1, 6, 3, 2, minus 4, 0. Okay, so first let's write down its cofactor matrix. So its cofactor matrix, so it's cofactor matrix. Remember that this is the matrix C, whose entries come from the determinants of submatrices up to a certain sign. So the first entry here is the determinant, the 1, 1 entry is the determinant of the 1, 1 submatrix. That's the determinant of 6, 3, minus 4, 0. The 2, 1 entry, that's right here, is negative the determinant of the corresponding 2, 1 subentry. So that's 2, minus 1, minus 4, 0. And the 3, 1 entry, that's going to be plus, I'll put the pluses to be explicit, plus the determinant of the corresponding 3, 1 submatrix. That's 2, minus 1, 6, 3. So these are just numbers, and this is the first column of the cofactor matrix here. Remember, let me get rid of this, but like, for example, where does this entry come from? This is the 3, 1 entry. It comes from looking at the 3, 1 entry here, and then you remove the row and column that contains it, and what's left is this submatrix, and that's the submatrix whose determinant you're taking. Okay, and that's just how you do it. You have to put in a certain sign. Alright, so let's keep going. So what does the middle column look like? So the second column is the same thing. Now you have the next entry is negative determinant, but now when you remove the 1, 2 entry, you have this submatrix 1, 3, 2, 0. This next thing will be positive determinant. When you delete the 2, 2 entry, you get the 3, minus 1, 2, 0. When you delete the 3, 2 entry with minus 4, then you get this submatrix 3, minus 1, 1, 3. So that's the second column, and now to do the last column, this will be positive determinant. When you delete the 1, 3 entry, you get the 1, 6, 2, minus 4 submatrix. You get negative determinant. When you delete the 2, 3 entry, you get the submatrix 3, 2, 2, minus 4. And when you delete the 3, 3 entry, you get the submatrix 3, 2, 1, 6. Okay. So that's what the cofactor matrix looks like, and we can just calculate everything out. When we do that, we see that we get, this is a positive 12, that is a minus, that becomes a positive, that becomes a minus, becomes a positive 4. Just be careful with double negatives, it's very confusing. That gives you a 6, minus minus 6, that gives you a positive 12. The next entry here, that gives you a minus 6, but there's a, the determinant is the minus 6 here, but then there's a negative, so that becomes a positive 6. Here, the determinant gives you a positive 2, and so you get positive of that positive 2. Here, the determinant in the 3-2 position, the determinant gives you 10, but then you have to make that negative, so you get negative 10. And now let's do the third column. Here's this determinant that gives you negative 4 minus 12. Negative 4 minus 12, that gives you negative 16. For the 3-2 entry, the determinant gives you negative 12 minus 4. That's negative 16, but there's a negative in front of it, so it becomes a positive 16. And last but not least, this entry, when you take the determinant, that gives you an 18 minus 2 is 16, and so you get a 16 here. So that's what the cofactor matrix is. That's the cofactor matrix of A, and therefore, the adjoint, so now that we have that written, so the adjoint of A, which is right here, so it's adjoint, so the adjoint is C transpose. So C transpose, that just means the first row, or the first column, becomes the first row. You can do it. I usually turn the column into rows, so that first column is 12, 4, 12, that becomes the first row, 12, 4, 12. The second column, 6, 2, negative 10, that becomes the second row. And the third column becomes the third row. So this is the adjoint of the matrix that we started with. 3, 2, minus 1, 1, 6, 3, 2, minus 4, 0. So that is an example of the adjoint of a matrix. So to construct the adjoint of a matrix, you first have to go through this tedious process of calculating the cofactor matrix, and then you just transpose it. So applying a transpose is such a trivial thing. Why do we need a new term for it? And the reason is because of this very, very important result. So this is a theorem. It says that if A is invertible, then we can actually calculate the inverse matrix is 1 divided by the determinant of A times its adjoint matrix. So this gives us a new method for calculating the inverse of a matrix. This is a very, very important result. So if A is invertible, then we can calculate its determinant. We can calculate its inverse using this method of using the adjoint. So this is why is this useful? You may say, how is this useful? So in practice, this is incredibly useful because in practice, you have some matrix, and so first you compute the determinant to see if it's invertible. But of course, in doing so, in calculating the determinant, you need the cofactor matrix. So in order for you to even see whether or not the matrix is invertible, you have to calculate its determinant. And to calculate its determinant, you have to find the cofactor matrix. So that means you already know the cofactor matrix. So then if the determinant is not 0, so if the determinant is not 0, well, you already know the cofactor matrix. And so therefore you already know, so you have the adjoint. Because the adjoint is just the transpose of it, and therefore you have the inverse. So in practice, if someone tells you that the matrix is invertible, then you can just use row operations to find it out. But if someone just gives you a matrix and you don't know if it's invertible, then you have to first figure out if it is invertible. In doing so, the only way we can do that is, well, to either find the inverse directly using row operations, or to calculate the determinant. So if you want to use the determinant, then you've already done all the work. Basically, once you figure out if it's invertible, then you are just one step away from calculating the inverse of it. All right, so let's go back to, let's do a few examples. So examples. So here's an example. Let's use the same matrix from the previous example. Over here is the matrix A, 3, 2, negative 1, 1, 6, 3, 2, minus 4, 0. Okay, so matrix A is 3, 2, minus 1, 1, 6, 3, and 2, minus 4, 0. And so we have that, and then we found that the cofactor matrix is 12, 4, 12. This is just work we've already done. You can just go back up and rewatch this to see where this comes from. Okay, so now what we can do is we can put these two together, so we can find that the determinant of A, we can expand along, say, let's go along the first row. Let's use the first row. So that means we're going to do 3 times 12 plus 2 times 6 minus 1 times minus 16. That gives you 24 plus 12 plus 16. 24 plus 12 plus 16, so that's equal to 64. This is, of course, not equal to 0, so A is invertible. Okay? And notice that in order to come to this conclusion, we had to calculate the determinant, and to calculate the determinant, we had to calculate the cofactor matrix. This is the cofactor matrix here. But since we've already done the cofactor matrix, we now know, so now we can find its inverse. By the theorem, we know that A inverse is going to be 1 over its determinant times its adjoint. Well, we already know that its determinant is 64, so it's 1 over 64, and its adjoint is just the transpose of that, so it's just 12, 4, 12, 6, 2, minus 10, minus 16, positive 16, positive 16. And that's it. That's the inverse. You could, simplify it if you wanted to, but that's just it. Remember, a matrix times a number, it just scales into it. So, this is just like the matrix 12 over 64, 6 over 64, minus 16 over 64. That's how you multiply a matrix times a number. You just multiply all the entries. 4 over 64, 2 over 64, 16 over 64, 12 over 64, minus 10 over 64, 16 over 64. And you can simplify this, but this is the inverse. So this is A inverse. Very cool.